Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. We had been discussing kinetics in our previous lecture, and in this lecture we are going to talk about acids and bases. Okay. Very important parameter is pH of any system, and today we are going to understand how pH affects the chemistry of any aquatic system. But before I move on to certain particular examples and how pH can change the composition and chemistry, we are going to try to understand very basics of acids and bases just to brush up your basic concepts, and then we are going to see how to write a few reactions, dissociation reactions. So, let us just start with the basic things. So, first of all, how do we define an acid? Okay, how do we define an acid? So, Arrhenius in 1887 proposed that an acid is a substance whose water solutions contained an excess of hydrogen ions. Okay. So, if you mix water in with an acid, then you will have an excess of H plus ions that will dissociate and form H plus ions. The excess H plus ions resulted from the dissociation of the acid as it was introduced into the water. So, when it is forming a solution, immediately it will start a dissociation reaction and it will dissociate producing H plus ions, that is very particular of acids. Another person, Bronsted, he gave the definition that acids are those compounds which can donate a proton to another substance which is a proton acceptor. So, in terms of protons, it is now being said. So, H plus again is basically a proton. Okay. So, you just say either it is in H plus term or in proton terms. Okay. But for our aquatic geochemistry, we are going to prefer H plus as our notation. In terms of notation, we are going to write mostly H plus when we are trying to understand acids equations. So, if you are trying to write the dissociation equation, then we are going to write HCl plus H2O, that is forming H3O plus plus Cl minus. That means, it will dissociate into H plus, and that H plus will again get attracted towards another water molecule forming that H3O plus complex. But again, that is a continuous breakdown will happen. So, there will be enough H plus ions in the system. So, you can either write H plus or you can write H3O plus. Okay. So, what is in terms of another acid, say for instance H2CO3. Okay. So, H2CO3 will react with water. So, carbonic acid reacting with water, one H plus ion will go out and it will form H3O plus, and the bicarbonate ion will be there, HCO3 minus. Okay. Again, in the next equation, this HCO3 will break down to form bicarbonate ion CO3 2 minus, and the other H plus ion will get released. Okay. So, there are two steps for 2 hydrogen, there will be 2 steps for carbonic acid. And if you take water, okay, so water can both be a acid and a base. It can, depending on the other compounds that is present with it, it can behave as if it is a acid or it is a base. Okay. Now, we are again, so in our aquatic geochemistry, we are going to use the Arrhenius form and we are going to write in this kind of dissolution equations. And how we generally write monoprotic acid, diprotic acid, triprotic acid. Okay. And what is the diprotic, monoprotic and all? So, monoprotic has only one proton to donate, a diprotic acid has 2, triprotic 3. So, that is how we denote the acid terms. Now, how we are going to write few basic equations. Okay, this is again very important, writing some basic equations for acid reactions. So, let us consider this acid, acetic acid. Okay. So, acetic acid, this is the formula CH3COOH is an example of a monoprotic acid, that means it has only one hydrogen to donate. Okay. And if we abbreviate it in terms of H and A, where H is my hydrogen that we have to donate, proton that has to be donated, and A is the base. So, this A term is my this base term, this entire thing CH3COO minus. So, that will be my A term. So, we are going to write in these terms. So, H, that HA is basically my H is my proton or hydrogen ion, and E is my conjugate base. Okay. So, for CH3COOH, CH3COO minus is my A. Now, we need to determine 4 components, 4 species. Okay. The first thing that we are going to determine whenever there is acid base reaction, okay, what we are going to determine is that HA is going to form this A minus, and there will be some H plus ions forming. But there is also going to be some HA terms which is undissociated, right. There will be some undissociated HA terms, and when there is dissociation going on, there will be reaction with water. So, water will form H plus and OH minus ions. So, there are 4 species. What are they? HA, whatever we are adding into the system, some of it will get dissociated to form A minus and H plus, and there will be an undissociated component. So, undissociated HA, newly formed A minus and H plus, then water will form H plus and OH minus. So, this is my species 1, this is my second species, this is my third species, and this is my fourth species. Okay. So, you have 4 components. So, your components are 4 components, HA term, A term, H plus term and OH minus term. Okay. Now, to solve for these 4 unknowns, we therefore need 4 equations, right. The number of unknowns should be equal to the number of equations. Okay. So, if you have 4 unknowns, we need 4 equations, and how, what will be those 4 equations? And again, in here I write it in terms of, so to just make it simple, okay, just to simplify the matter, now we are going to neglect this activity correction, and we are going to assume that the activities are equal to the concentration. Okay. This definitely holds true for dilute acids and also for very concentrated acids. Okay. So, for most acids we know the activity coefficients and you can do the corrections, but for now we are going to neglect these activity corrections, okay, and we are going to consider that the activities are equal to the concentrations. Okay. So, the 4 equations that we need are, the first equation is the reaction, okay, that is the HA, how we are going to form H plus ion and the anion. So, that is our basic equation. The second equation is related to the equilibrium constant. So, if the reaction is at equilibrium, then how do we write the reaction? So, it is equilibrium constant is equal to H plus into A minus divided by HA. So, this is when my reaction is at equilibrium. Okay. So, this is at equilibrium, you can write this reaction. Then the mass balance of A. Okay. Other thing is the mass balance, that you know, that is for sure. So, the concentration of A term. So, A will be there in some undissociated HA, A is there in undissociated acid and also as the base in the anion form. Okay. So, the total concentration will be the undissociated acid plus the base plus in the anionic form. Okay. So, that is the total concentration in terms of the E term. And the fourth equation will be related to the charge balance of the equation, and that is the total positive ions is equal to the total negative ions. See, whenever you see a solution, do you feel any electrostatic effect? Do you feel any charge in that, do you feel any charge? No. So, always there is some charge balance going on. Okay. The charges are always balanced in any aquatic system. So, therefore, this charge balance is our final fourth equation, where all the positive ions is equal to all the negative ions. Okay. So, by solving, okay, by any kind of mathematical equations that you want to do, any kind of calculations that you want to do, by doing these kind of substitution and all that, you can find out whatever the values that you want to look. So, this is considering monoprotic acids. With diprotic acids, triprotic acids, the number of steps will be increasing. Okay. The equilibrium constant will look different, the mass balance will look different, the charge balance will look different, because there will be more species getting involved. So, this is the very basic, for basic understanding you can take in the simple acids. Okay. Say you consider HCl and you write the equations. Okay. So, and you go on adding. So, for bicarbonate ion, bicarbonic acid. So, for carbonic acid there will be two dissociations, right, first to the bicarbonate ion and then again in the next step it will be to the carbonate ion. So, there will be 2K. Okay. So, based on that you will write the equations for different kinds of acids, be it by diprotic acid or triprotic acids. Now, let us discuss a little bit on the dissociation constant, that is Ka value. Okay. So, the equilibrium dissociation constant Ka value. What information and how do we use it? Okay. Now, the Ka, okay, so the Ka we use, the term Ka refers to the equilibrium constant value when an acid donates a proton to water. Okay. When there is an acid donating a proton to a water. The Kb term is the reaction when a base accepts a proton from a water. Okay. So, accordingly, so it is just acid and base. So, Ka and Kb values vary whether you are writing the equation in terms of Ka or you are writing that in terms of Kb value. Okay. Now, the value of Ka or Kb is the will give you the strength of the acid or the base. Now, what do you mean by the strength? That means how strongly it will donate a proton, its tendency, how strong tendency it has either to donate a proton or to accept a proton. So, the higher Ka values are very strong acids, while the lower Ka values are the weak acids. And this very strong acid will have the tendency to donate all its protons. So, all the H plus will get dissociated and all it will get, it will be in the H plus form. As compared to a weak acid, it will not dissociate completely, its tendency will not be very strong to donate all the protons. So, there will be some undissociated acids. What will be a strong base? A strong base will quickly accept all the H plus ions and will start forming the salt. Okay. So, base is just opposite, it will start accepting all the H plus ion and it will be forming a salt. Now, Ka is usually expressed in log. Okay. So, log of Ka is the pKa value. Okay. So, pK is, what is pKa? pK is the minus log of Ka. This is the negative log of the equilibrium constant. A very strong acid dissociates completely at almost all concentrations. So, even if the concentrations are very high, it will dissociate completely. And a weak acid does not dissociate completely, leaving some undissociated acid in the solution. Okay. And now, as a rule of thumb, the strong acids have a weak conjugate base and the weak acids produce a strong conjugate base. Okay. So, that is just a rule of thumb. Now, let us see some other strong acid base calculus. So, a strong acid is reacting with a strong base. So, strong acid and strong base calculations. Okay. Now, the most commonly found acids in aquatic systems are nitric acid and sulfuric acid, and they can either come from acid rain, that is dissolving all the industrial gases or some. So, basically there is a lot of pollution due to anthropogenic activities. It can be due to burning of biomass, it can be due to any kind of industrial activity. So, different kinds of activity release nitrogen oxide, sulfur oxide, simple like automobile exhaust, automobile emissions, they will give out NOx and SOx compounds. Okay. So, they are there in the atmosphere, they will dissolve in water and they will form this acids, nitric acid and sulfuric acid, and they will come down with the rain. Okay. So, we call them acid rain, right. And if it is there in the soil, okay, it will interact and all that. So, it's so nitric acid, sulfuric acids are very common, and sometimes you can have the usage of very particular acids in industries. Okay. So, HCl is very very commonly used in industries and also particularly for the well activities. So, if you are trying to dig up a well for extracting groundwater, many times you will see that there is some calcite deposits are there. Calcite, if there is a lot of carbonate rocks are there, then certain times HCl can be used to ease up the digging process. Again, so if you are using HCl, it is a very strong acid. So, there will be a higher Ka value and there will always be more products than the reactants. So, all the reactants will be dissociating and there will be more products, and that means the reaction very fastly proceed to the product side. Okay. The reaction rate will be very high, and the dissociation of strong acids is generally exothermic in nature. That means it will add to a lot of positive entropy. The heat of the system will increase, it is exothermic reaction, and that will increase the entropy of the system. Okay. And the release of heat is generally from the hydration of the proton to make a hydronium ion. Okay. So, these are the few basic equations that we write. Okay. So, first is HCl, which produces H plus and Cl minus, and if you are writing the Ka term, that means with respect to the acid, you will write H plus into Cl minus divided by HCl, and this we know has a value of 1000. Okay. So, the Ka value is 1000, and so if you write it in log terms, the Pk value comes minus 3. So, Pk value comes minus 3. Okay. So, what does that mean? What does this equation mean? This equation means that the product of the hydrogen ion and the chloride ion is 1000 times the concentration of free HCl in water. That means, basically this is negligible. It is 1000 times more available as H plus and Cl minus. Okay. And this leads to the very basic assumption to simplify our acid basic calculations, that the strong acids dissociate completely in dilute solutions. Okay. It will dissociate completely in dilute solutions, that means this terms is very negligible, okay, and you can remove this term. Okay. And even for mass balance, the chloride ion concentration is very great as compared to the HCl concentration, the undissociated HCl. This is the undissociated HCl concentration, okay. And therefore, the concentration of total chloride in that solution is equal to, if you have that, then you can just neglect this term, okay, you can just neglect this term and it will only depend on the chloride concentration, only depend on the chloride concentration. So, this is a simplification, okay, for stronger acids. So, this is just showing which are the strong acids, okay, and the intermediate acids in natural systems. You have perchloric acid, which is very strong, -7 pK value, that means the Ka value is 7, 10 to the power 7. Okay. Hydrogen chloride, as just we said, -3. So, different acids have different pK values. Okay. Then now let us see some weak acid base calculations. Okay. So, for weak acid bases, just that they do not dissociate completely. So, these are the examples of certain weak acids, okay. And solving these equations can become a little more complex, okay. So, solving these equations can become a little more complex, and therefore, we have to use more simplifying assumptions. We have to start using more assumptions in these kind of systems. For example, if you have hydrofluoric acid, acetic acid, okay, and you can see that for some acids there will be a pK2 value, pK3 value, depends on the number of dissociations and all that. Okay. The small pK values means that the concentration of the reactant is greater than the products, and therefore, there is not complete dissociation, that is, the reaction does not proceed very far to the right. Okay. The products are not too great as compared to the acid. An example of this, hydrogen sulfide is produced by sulfate reducing bacteria in anaerobic groundwater conditions, okay, in anaerobic in anaerobic conditions. Okay. So, hydrogen sulfide is a very weak acid, okay, and this is the breakdown of hydrogen sulfide, okay. H2S is breaking down to H plus and Hs minus, and the K term, okay, the first value, okay, K1 value is H plus into Hs minus divided by H2S, and that is something as 10 to the power minus 7.1. So, when you have minus 7.1, the pK term becomes positive. So, pK term is positive 7.1. Now, what is the understanding of this? Now, how do we understand that in any system, in any aquatic system? That means, the fundamental relationship with weak acid is that the extent of this reaction is or could be understood with relevant to the pH of the system. Okay. How far the dissociation will happen, that now we can relate it with the pH. If the pH is very less than the pK, then little acid will dissociate. If the pH value is lower than the pK value, then there will be no dissociation, okay. It will be the little acid will dissociate. That means, the water is already slightly acidic. If pH is low, then the pK value, say suppose if pH is already at 6.5. So, slightly acidic composition, then there will not be much dissociation, little acid will dissociate. As the pH value moves towards increases, so as the pH increases, that means it moves towards a value say such that pH is equal to 9. So, it is more alkaline, then more acid must dissociate to maintain the equilibrium. You understand? If the pH is less than the pK, then there will be little dissociation, but if the pH is high, okay, if the pH is more, then that acid needs to dissociate to maintain the equilibrium. Okay. So, the relationship between pH and pKa for weak acids is this. So, pH is equal to pKa plus log of salt plus acid. So, the conjugate salt that will form divided by the acid concentration. And with weak acids, when the pH is equal to pK, the activity of the acid is equal to the conjugate base. So, basically what will happen is, so pH is equal to pK, right. So, this term becomes 0, right, this terms become 0. What do you mean by this term becoming 0? That this is equal to, the salt is equal to the acid concentration. So, that is just an example, that is for H2S at pH 7.1, H2S is equal to Hs minus concentration. So, that is an assumption that you can start making, that if the H plus, if the pH of the solution is equal to 7.1, then this concentration is equal to this concentration. Okay. Strong acid and weak base mixtures. Now, these are again very complicated, okay, and complication depends on how it is buffering and how is the dissociation, whether it is completely dissociating or not. Because if you have a weak base, how that is going to accept the proton, that how to what level it is going to accept, that becomes a question. So, in natural waters we have this more, we have more complex systems, right. Natural waters are more complex systems. So, it is a mixture always of either weak acids and bases, and whether it is a strong acid, whether it is a weak acid, whether it is a strong base, weak base, we find all of them in a system. Okay. And in generally the buffering, the pH buffering, we need to understand that, okay, how pH buffering will happen. Okay. And to find that, we need to find out the components. So, we try to find out, oh, is there possibility of bicarbonic acid formation, or is there any anaerobic conditions, okay, is there any alkaline groundwater coming in. So, what is the pH of the system, how it is changing. So, all this pH buffering of the system, is there any carbonate in the system, okay. So, all the buffering activities you need to understand. So, what is a buffering system? A buffer solution is something that will make the system to remain at a stable composition even when some little additions and removal is going on. So, various components are coming in and getting removed, but the buffer is going to maintain the pH of the solution. A solution buffered at a particular pH will contain an acid that reacts with any strong base added to the solution, or a base that reacts with any strong acid to the solution. So, if you see that the solution, whatever aquatic system you are taking, that is showing a very strong buffering. That means its pH is extremely constant. Okay, its pH is just not changing. Then you know that the buffering system is very strong. That means either there is any very strong base there, that means any strong acid coming in to the system, it will very quickly reduce its impact, or there is a very strong acid there that is continuously interacting to remove the base from the system, so that the pH is maintained. Okay. And the pH of a buffer solution, for that you are going to use this equation. You can use this equation, pH is equal to pKa plus log of salt divided by acid, assuming infinite dilution. Okay. That means it is a very diluted solution. This is considering a dilute solution. Okay. Let us go on to some important processes where we see such pH changes. Now, let us move on to the more practical aspects. Okay. How some reactions are going to change the pH of any system. If there is first equation, a very basic equation, that is carbon dioxide dissolution in water. So, carbon dioxide gas dissolves in water to form CO2 aqueous, okay, and that reaction forms the bicarbonic acid. Okay. And if that is happening, the dissolution is happening, the pH will go down. If it is a more forward reaction, so this indicates the forward reaction, right. This indicates a forward reaction. The forward reaction meaning carbonic acid is getting formed. So, if an acid is getting formed, the pH will move towards more acidity. So, the pH goes little down. Just the opposite, if the reaction is going in the opposite direction, where there is carbonate release is happening, okay. Carbonate is getting released from the system. Okay. So, it is a source of carbon dioxide. Okay. Then the pH will move up. So, for the backward reaction, the pH will move up, up meaning it is moving towards more alkaline solution. Photosynthesis, if it is photosynthesis, again carbon dioxide is taken in, then again the pH will, for the forward reaction the pH is going up, and the backward reaction it is going down. Methane fermentation, okay. Methane fermentation, methane is interacting, again there will be, finally it will produce carbonic acid. So, that will again let the pH to go down. Okay. Nitrate uptake and reduction, okay. It will form nitrate ions, it can form nitric acid. So, that again will form, can lead to the formation of nitric acid and carbonic acid. These H plus ions that is getting released during this reaction, as well as the dissociation of these further, will lead to more pH. Okay. So, pH will go up. Okay. Then sulfate reduction, again sulfate, if it is getting reduced, again some H plus ions and some Hs minus ions will be, that is going to form. Carbon dioxide is going to get released. So, what will that do? That will pull up the, it will make it more alkaline. The pH is going up, up means more alkaline. Carbonate mineral dissolution, if carbonates are getting dissolved, okay, if the reaction moving in this side, it is going up, it is alkaline if carbonate is dissolving, and if it is precipitating, then it is going down, it is more acid. Common ion driven calcite precipitation. So, basically different kinds of weathering reactions, calcite precipitation, carbonate mineral dissolution. So, all of them are changing the pH. Okay. All of them are changing the pH of the system. Okay. And by following this simple equations, you can try to find out whether the pH is supposed to go up or it is supposed to go down. And again, we need to understand all the products, not simply this one. So, how is this going to finally end up in the system? Okay. How is this CO2 going to end up in the system? Okay. So, all of that we need to understand, and then this is finally what is the result. Okay. So, with this I will stop in this lecture. In the next lecture we are going to carry on with the more practical impact of pH on controlling the aquatic compositions. Okay. We are going to see some specific examples, and we are going to see why pH is important. Okay. With that, thank you.